And today we kind of have like a panel discussion, public talk this time around. And so we have Professor Jonathan Gagné from UDM. And we also got Casey Brinkman, a TSI Postdoc Fellow, and then they're going to be discussing about exoplanets. So it will be about 30 minutes presentation for each. And then at the last half an hour of the talk, the public can just like ask questions and they would like basically answer to you guys. So just before we start, just kind of want to talk about the code of conduct for our events. So we want this to be a welcome space for everyone. So if you feel any sort of uncomfortable or like anything that we need to be know of, please let us know. There are volunteers that will help you out if needed. And anything else that you want to email us, here's a link. If you have any question, and then or even for kind of future recommendation, and then like the improvement of the talk. But other than that, Jonathan, I'll let you take it away.
So can you hear me well? I think it's working. So thank you everyone for coming tonight. So I'm gonna talk to you about what we currently know about free-floating planets, quote unquote. You'll see why I put quotes here in our neighborhood of the galaxy. So just a small overview of what I'm going to talk about tonight. So I'm gonna talk about what planemos are and why they're awesome, how we find them in space, how we find new ones, and what is currently known scientifically about these odd objects. And I am also going to present to you some of the recent cool discoveries on this topic. And as you heard earlier, we will also answer a lot of questions together with Casey after the talk. So let's start with what are planemos. So in order to speak about planemos, I also want to speak about a different type of object that is called a brown dwarf. You might have heard about brown dwarfs. They're a bit more popular than the planemos, but they are also obscure, both of them. And they are somewhat similar objects. So we're gonna start discussing brown dwarfs a little bit. So sometimes brown dwarfs are called super Jupiters or failed stars. I will let you guess which definition I prefer of these two. But basically, they are objects quite similar to Jupiter in terms of their size, but they can be much warmer and also much more massive. They just have a very similar size. And they also have probably very beautiful clouds on their surface. We know they have all sorts of clouds and storms. We've never actually seen them, so that's why I'm saying they're probably beautiful, but they have very complex atmospheres, much like those of giant planets, and they are made of gas, like Jupiter, Saturn, Uranus. However, these objects can form just like stars. So if you weren't aware, stars form in giant molecular clouds. And this is a simulation by the StarForge collaboration, which is actually a physics simulation that just happens to be very beautiful, showing stars getting born in a molecular cloud. But what you're not necessarily seeing here is that some of the very faint dots in this image might be brown dwarfs. So you're not just forming stars from a molecular cloud, you're also forming brown dwarfs. And these objects, we can find them alone in space, like the case I'm showing on the lower right. However, we can also find them in orbit around the star, like the case on the upper right that I'm showing here. This one has a beautiful name, LHS 2397b. This is a brown dwarf around the star. And you can also find binary brown dwarfs, meaning you have two brown dwarfs that orbit each other. And the nearest known brown dwarf is actually a binary. This is the one I'm showing on the lower left here. It's called Luhmann 16. So there is a fundamental difference between brown dwarfs and planets, and it's about their mass, basically. So if you find an orbit, if you find a brown dwarf in orbit around a star, The reason why it's not a planet is really about its mass, basically. So we have decided as a scientific community to put this limit at 13 times the mass of Jupiter. And the reason for that is because our physics models tells us that something special happens at that specific mass. Basically, objects more massive than 13 times the mass of Jupiter can burn deuterium in their core. This doesn't do much because it's a very rare element and it only gives it energy for a very short amount of time. So it doesn't change much in the life of a brown dwarf, the fact that it burns deuterium, but it's kind of a clean definition in terms of mass that separates brown dwarfs from planets. So if you find a 15 Jupiter mass object in orbit around the star, you would call it a brown dwarf. If you find a 10 Jupiter mass object around a star, you would call it a planet. And at 75 times the mass of Jupiter, there's something much bigger that happens. It's the nuclear fusion of hydrogen. So there you have a very big difference because it gives the star a lot of energy for a very long time. So the star can remain hot and bright for a very long amount of time. Yes?
Yeah, sorry, I thought that it takes the more massive star is, the more heavy elements it can like do fusion. So
Yes.
why are brown dwarfs capable of just using deuterium?
Yes, because deuterium is not really like one of the heavier elements in the periodic table. It's an isotope of hydrogen and it's less stable, basically. So that's why brown dwarfs are able to burn it despite it's not hydrogen, it's because it's actually more fragile. But there is so little of it that stars also burn it. But you don't really know this because it all happens so fast and it doesn't change much. It's the hydrogen that is very abundant and that gives a lot of energy to the stars. And yes, massive stars, especially when they start depleting hydrogen, they start burning other elements that are more massive. But here we're really just focusing on the difference between a star and a brown dwarf. So in order to understand why this example I gave earlier, LHS 2397, why its companion is not a planet, we can examine the definition of an exoplanet that the International Astronomical Union gave us. This companion has a mass of about 70 times the mass of Jupiter, so very close to the boundary between brown dwarf and star. So the International Astronomical Union decided that in order for an object to be a planet, here I'm not saying exoplanet, I'm talking about planets in the solar system, an object must be in orbit around the sun, massive enough to have a round shape, and it must have cleared its orbit of debris. This last one is why Pluto got demoted to dwarf planet instead of just planet, but that's a topic for a different day. And in the case of exoplanet, exo means outside. So the definition of an exoplanet is that it's in orbit around a star instead of the sun. But then they added something a bit sneaky to the definition. There's also a mass constraint now. The reason we didn't have that for the definition of a planet is that we simply don't have a brown dwarf in the solar system. So we didn't have to specify that. But now we do, because there's a lot of stars with brown dwarf companions. So we need to distinguish them. But then these two definitions, they are a bit complicated. They're kind of imperfect, but they don't cover something very interesting. What do we do with an object that has less than 13 times the mass of Jupiter that is not in orbit around a star? It kind of doesn't match any of these definitions, and we didn't really decide on a definition for these objects yet because they're very recent. We haven't studied them for a very long time. We've known them for less than 20 years with certainty. So we started calling them planetary mass objects in science publications because we don't really know how to call them and they have a planetary mass. So it seems like a good word. And that got contracted into planemo, which is literally just a shorthand for planetary mass object. So planets and planemos kind of fall in the same mass category with no burning whatsoever in their core. And then brown dwarfs do deuterium burning for a short amount of time. And we sometimes use the term substellar objects to talk about brown dwarfs, planemos together. And now there's a question of how these objects formed. Let me try and start this. Okay. So let's imagine you have a binary star with the red and blue dot. This is a simulation of the orbit of a planet around these. These types of simulations tell us that sometimes a planet can be ejected. We've never observed that in a very direct way because it would be very hard to catch one that was just ejected and then we could trace it back and say, oh, it comes from this star. We are not there yet, but we suspect that this happens. However, they might also form like stars, like brown dwarfs. So there is some questions about their origins, and the answer might also very much depend on the type of planemos we are looking at. So it's possible that most of the 10 Jupiter mass planemos form like stars and brown dwarfs, but most of the less than 1 Jupiter mass planemos are actually ejected planets. So this gives us even more questions about how to call these objects, what they are. So this makes it very hard to define them. Now I want to talk a little bit about their properties. So as you might know, what determines the color of a star or a substellar object is their temperature. It's a bit like the same principle as a hot iron. So as you move from hot to cold, the light is going to be emitted from the blue to the white, yellow, red, and even infrared light. In the case of brown dwarfs and planemos, we are into the infrared domain. So it's much better to use infrared cameras to study these objects rather than visible light cameras. And this is part of the reason why the study of brown dwarfs and planemos is so young. It's because infrared detectors is a relatively young technology. So we started getting access to these in the 90s and 2000s. And so the quality of the detectors got good enough to detect them. So in order to understand the properties of these objects, the first step is you go at a telescope, you take the light that you get from the object, and you split it across all of its colors. You can do this with a prism, like in the Pink Floyd logo, but there are also other methods to split the light among all of its colors. And you measure the intensity of each different color. In the case of a brown dwarf, the most intense part would be infrared. So you need a detector, not your eye, to measure it. And from this distribution of colors, you can guess the temperature of the object. But we have a problem with substellar objects. They do not do nuclear fusion. Brown dwarfs do it for a very short amount of time. That's why I drew the line here a bit flat at the beginning. They start with a quite warm temperature that is the result of the gravitational energy of the molecular cloud getting transformed into kinetic energy as it forms. So it gives the object some temperature. And the more massive it is, the hotter it starts. But then it just cools over time. So you get these tracks as the object ages. It just gets cooler and cooler. So what happens when you know just the temperature of an object? You don't know if it's an old and massive brown dwarf or if it's a young and low mass planet, because both would have the same temperature. So in order to know what you're looking at, you need to know their age. And in the case of an isolated object like these, you cannot use Kepler's laws to derive the masses. So you really are left with needing the age to understand these objects. So we have models of the physics of these objects, how they cool down over time and how their atmospheres and their clouds slows down the cooling. And we have all of these models we can compare with the data to determine what the mass of our object is, but we need to know both the temperature and the age to do this. And if we want to compare an object with a massive gas giant exoplanet, for example, we would like to focus on a planemo that has a 10 Jupiter mass, for example, not 60 or 70 Jupiter masses. So the first step we need is knowing the age of the object so that we know what type of object we're looking at, what mass it has. And this is one of the reasons why my research group is very interested in the study of young stellar associations. This is an example of a young stellar association that our group discovered. This was actually discovered by my PhD student, Leslie Moranta. And we realized that Lumen 16, the nearest brown dwarf, is part of this group. And so because of that, we knew that it has 600 million years old, and we were able to know its mass because of this. In this case, it's a brown dwarf and not a planemo. So how can we find new brown dwarfs and planemos? There's a question here. Yeah. So it's basically a group of stars that are born together, and they move all together in space for the first few hundred million years of their life, basically. So if you spot stars that are all moving together in space, you can guess that they all have the same age, and then you can derive this age by studying all of the stars in the group. And this is a bit subtle, like in this example, the brown dwarf is not actually in orbit around any of these stars. It is just moving in space along with them. It's very far from the stars, and it's not gravitationally bound. So all of these stars are independent of each other. They're just like siblings. They're moving along in space in the same direction. So in order to find brown dwarfs, we need, or substellar objects in general, we need to remember that we can only detect the nearby ones because they are very faint, and their light is emitted in the infrared. So the key is to take an infrared survey of the whole sky and look at images in the survey that were taken at different epochs. And you are looking for something that moves very fast because the object is close to us. Everything has motion in space. So the closer it is to us, the faster it will appear to move. And then the second step is to take a visible light catalog and to double check that it's not a star, that it's not visible in the visible light catalog. So it should be invisible in visible light, and it should be very bright in the infrared catalog. You can also play this game yourselves. You can try to find new substellar objects with this Zooniverse project called Backyard Worlds Planet 9. You can also try to find Planet 9, but this is a bit more of a long shot. In terms of substellar discoveries, this collaboration has already discovered more than 3,000 brown dwarf candidates. A lot of them are probably planemos, and I'm actually working with the science team to determine which ones that they're finding are planemos rather than brown dwarfs. And it's a very successful mission. So if you want to try it, just Google Backyard Worlds Planet 9 and you'll find it out. So someone might say, why are you interested? They're not even planets. They're not even exoplanets. So what do we gain from studying these objects? So remember when I said earlier that we can take the light from one of these objects and split it across all of its colors? If you measure the intensity of every color, you get what is called a spectrum, like the one I'm showing here. And these things can tell us about the chemical composition in the atmosphere of an object. And you'll hear more about that in the second talk, obviously. But here I'm showing one of the best spectra that we have for a hot Jupiter, for an exoplanet, that was obtained with the James Webb Space Telescope. And it allows us to see things like water emission in the spectrum. So we know there's water in the atmosphere in gaseous form, but it's very hard to go into the very precise details because we are so blinded by the star of an exoplanet, because it's always right next to a star that is so much brighter. So our instruments get completely blinded. So we need to use very difficult techniques to mask the light of the star. And what is fun with planemos is that we don't have this. the planemos are hard to find at first, but once you found one, you can point a telescope at it and get a very high quality spectrum. This is one example that we got for a planemo. And it might look like this is a bit noisy, like there's high and low lines in there, but you can zoom in this region here and see that it's not noise. It's actually real data that we have in there. And we can really constrain the atmospheres of these objects. And if we can study 100 different planemos and really understand what their clouds are, all of the possible different atmospheres, it's going to tell us so much about exoplanets. And then when we get the much more difficult spectra for exoplanets, at least we know the possible atmospheres that can be out there, and we better understand all of the processes that can happen, what the clouds do when an object is cooler or hotter or with a different composition. It can really help us explore all possible atmospheres out there in space. So what do we currently know about these brown dwarfs and planemos? So earlier I mentioned groups of stars that form as siblings. So this happens in a giant molecular cloud, like I mentioned earlier. So before the stars form, the cloud is on an orbit around the Milky Way. And after it collapses into stars, the stars have some random motion, but mostly they retain the orbit of the molecular cloud. That's why they move together in space until they are mixed up by the Milky Way after doing a couple different revolutions and getting tugged on by the other stars or by the other molecular clouds that they cross. So in order to find the objects that are members of these groups, or in order to even discover these groups of siblings, we need to know the 3D velocities of stars. And this is actually very hard to do. And until recently, we really did not have amazing data to do this. But this changed a couple years ago with the European Space Agency mission Gaia. So Gaia is a space satellite that actually measured the precise distance and the motion of 1 billion stars. And it is the data that this spacecraft got is still being analyzed, and new releases are coming up still. But this really revolutionized our understanding of the kinematics of stars, of how stars move. And for example, the nearest open cluster called the Hyades, some researchers found a massive structure around it that is actually made up of members of the Hyades that are getting stripped away from it. But they are originating from the Hyades, they have the same age, and they are still moving together in space with the Hyades. And something similar was also discovered around a lot of open clusters around the sun. Open clusters are basically families of stars, but just more dense. There's a lot of stars. And all of these extensions around these clusters, those are all new grounds where we can find planemos, because we know the ages of all these things that move together. So they're all new places where we can assign a mass. If we find a substellar object in there, we might have thought it's a brown dwarf before, but now we know it's young, and now we know it's a planemo when we find them in these groups. So in parallel to all of these new discoveries that are being made about the kinematics of stars, a lot of new brown dwarfs are being found. One of the methods is the Backyard Worlds Planet 9. And we now have about 3,000 brown dwarfs that are confirmed. So earlier I said the Backyard Worlds project has found about 3,000 candidates. So it's in the process of actually doubling the number of brown dwarfs that we know, which is very significant. So in order to deal with all of this, in my team, we built a database to really catalog all of the known groups of siblings of stars and all of the known brown dwarfs with all their known properties, so that we can really digest all of this massive amount of data. And in my team, I currently have 3 members working with me. There's Leslie Mavanta, who is working on finding these new groups of stellar siblings and on the ages of stars. She's doing a PhD. We have Louis-Philippe Coulomb, who is a postdoc, who is working on characterizing the atmospheres of these planemos. So really modeling the physical processes to understand where the clouds are and what are they made of and what is the chemical composition of these planemos. And we have Azul Ruiz-Diaz, who is doing a master's on finding some of the new planemos. So as you can see, all of this is tied together. It's like all different aspects that are directed into the same goal of understanding these atmospheres. So now I will just briefly mention a couple of cool recent results about planemos, and then I will let Casey give you the next talk. So we now have a couple different examples of planemos that have been observed with the James Webb Space Telescope to really do a deep dive in their atmospheres and understand what it's made of. And we now know that there are enstatite, forsterite, quartz, and iron clouds in these objects very often. So it's very funny if you go, I have collaborators at the AMNH Museum who work with me on these things. And there's a location in the museum where you can see all kinds of minerals. There's like a big window with hundreds of different minerals. And they're all in brown dwarf atmospheres. Like you read all of these, these tags on these minerals, and they can all form in the atmospheres of brown dwarfs, which is kind of crazy. But these four that are shown here are really, they often show up and they are very important. They affect the data a lot. And with our team, we have just published a new paper that you are probably gonna hear about in some press releases soon, where we have actually doubled the amount of current planemo candidates in our neighborhood. So we used to know approximately 50, and now we are closer to 100. So those are a lot of new exciting targets for James Webb observations and deep characterization of their atmospheres. Something really cool that happened recently also is that 2 planemos have been identified with probable aurorae on them. So we know this from we don't have actual pictures, these are artist renditions, but from the modeling of their atmospheres, there's something very weird happening where the top layers are warmer than the bottom layers. And usually this happens if you have a star that heats up the top of the atmosphere, but here there's no star. So it could be aurorae. And then the question is, but what is causing these aurorae? And one of the possibilities could be moons around them, but we don't yet have the means to test that idea and detect the moons, but we are trying. Another really cool result that happened recently that is not at all from my team and not my expertise is the discovery of planemos with a method called gravitational lensing. It's kind of a complicated method that I won't explain in details now, but you can ask questions about it later. But basically you're just staring at a lot of stars and you're waiting for a free-floating planet to pass exactly at the right spot so that its gravity focuses the light of a background star on you exactly. And then for a very short moment, the background star becomes brighter and then fainter again. And normally you wouldn't know if it's a very massive object that is further away, or if it's a very low mass object that is closer to you. But in this particular case, they were able to observe it with 2 different observatories that are so far apart that they determine the distance. So they observed it with the Gaia spacecraft that is very far from the Earth and from the Earth. And they could measure its mass for the first time. So we had a lot of detections of objects like that where we thought probably this is a planemo, but we're not sure yet. Like we had a dozen different ones, a few dozen actually. But this one we know it has the mass of Saturn. And this is really cool because all the other planemos I was talking to you about, they all have masses between like 3 times the mass of Jupiter to 10 times the mass of Jupiter. This is 0.2 times the mass of Jupiter. This is tiny. This is a very, very small planet, and it probably cannot form like a star. So this might really be an ejected planet that they have observed. The problem is we don't see it anymore. With this type of observations, you just get a glimpse and then never see it again. So, unfortunately. So that's it. And I will now share Casey's talk with you. Okay, let's see if I can do this a second time. I think I know it. Here. Presenter. It's not presenter view. Oh no, I did this last time. This. Yeah, that's what I next step. Oh yeah, okay, I know what we did. We did presenter view, but when we did this, it wasn't like I know what to do. Presenter view, I take this away, and then I go here, I do share, desktop 2, and before I share it, I'm not sure which one I should do first. Share, and then this. And then let's just see here. Yes, let's go on. Oh, it's because the Zoom is in full. Oh, sorry, that's not good for you. Zoom is in. How can we take Zoom away from full screen?
Take Zoom away from full screen.
Yeah. I just need it to be in the window.
Zoom is not in full screen.
Okay, that's good. Oh, okay. Can you? Oh, yeah, that's gonna work. Okay, so now we need to go here. Then bring the presenter view here.
No, well, actually, hold on.
Yeah.
Just checking on this.
Okay, now I just need to share the right screen here. Get it.
Oh no. No, YouTube just play.
I think it's good.
Oh, hold on.
So you might just have to click here to
Okay,
be
it
able to
works.
do next. Yes, now you can do next. So you need to use tiny arrows here. Oh, yes.
Okay. All right. I turn on.
I know you need to turn it down. I turned it down.
I turn it back. It just doesn't sound like it's working.
You gotta be really close.
Oh, okay.
There.
Oh, there it is. Okay. Well, hi everyone. Thanks for that amazing first talk from Jonathan. My name is Casey, and I'm a postdoc at McGill, working with Nick Cowan's group. And I'm going to talk about the other end of exoplanets, which is the smallest ones, and the inextricable link between planets and their host stars. So I wanted to start my talk by saying that I do what I do as an astronomer because my mom was obsessed with a man named Carl Sagan. And the moment I knew I wanted to be an astronomer was when I was watching the OG Cosmos, of course, and I heard Carl say that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, and the carbon in our apple pies were made in the interiors of collapsing stars, and we are made of star stuff. This means that every element heavier than helium is the result of stellar fusion from long dead stars. The lives and deaths of stars are what enabled the universe to build the sun, the earth, the solar system, and all of us sitting at McGill listening to me talk. And so that the elements that are fused during the lifetime and during supernova of a star become the nebular material from which future star and planetary systems form. So, what is our solar system made of? The sun, because it's a star, is predominantly made of hydrogen and helium, with trace amounts of heavier elements present in the stellar atmosphere, such as carbon, nitrogen, etc. Because the sun and the planets are born from the same primordial cloud of gas and dust, it's intuitive to assume that the chemical compositions of each might be similar. And this is in fact what we see for the gas giants in our own solar system. For instance, Jupiter has the same ratio of hydrogen to helium as the sun, 90% hydrogen, 10% helium, and it has similar ratios of the trace heavier elements as well. But I don't care about giant planets, and neither do you right now, because this is a talk about rocky planets. So let's zoom into the terrestrial planets of our system. And we see that, contrary to the other ones, these are largely devoid of hydrogen and helium, and they're too low mass to be able to hold on to these. Likely they formed with some hydrogen around them initially, and the sun was able to dissipate these envelopes very early in this planet's history due to radiation. The Earth is predominantly composed of an iron core and a rocky mantle. While we also, on the surface of the planet, know that we have oceans and an atmosphere, these aren't actually substantial portions of the planet's mass and its bulk composition. So for right now, we can pretend that they don't exist, and it's just an iron core and a rocky mantle. And despite this lack of hydrogen and helium at the surface, you might think that the rocky planets in the sun are not composed of the same materials at all, but you might expect that they have the same ratio of iron in the iron core to rock building abundances, such as magnesium, oxygen, or silicon. And in fact, this is what we observe. The ratios of iron and most major elements composing the mantle of the Earth mirror those in the sun to within a few percent of each other. Not only that, but we can observe similar ratios on Venus, Earth, and Mars, indicating that most of the terrestrial planets in the solar system have the same composition as the sun. And you'll probably notice that I left out one planet in particular, Mercury. Mercury is very different than the rest, and it has a much larger iron core relative to its rocky mantle. And it differs from the sun in ratios of iron to oxygen, silicon, and magnesium by 200 to 400%. So obviously, this is an anomaly in our solar system, and it means that something had to happen here to enrich Mercury and iron relative to rock. This means there's lots of different theories. We don't actually know what formed Mercury, which is kind of odd. Most likely, it could have been a series of giant impacts. But measuring the composition of a planet, in particular its ratio of iron core to rocky mantle, relative to the composition of its host star, can tell us something about the formation and evolution of that planet. Does it have the primordial composition of the system, or has it been processed in some way? And we now know more than just our solar system. We have discovered over 6,000 exoplanets so far. Of these, roughly 1,000 are roughly Earth-sized, between 1 and 1.5 times the size of the Earth. Most are extremely hot, but there are several that are about 200 that orbit in the habitable zone around their host star, indicating that we know of 200 planets that are roughly Earth-sized that we think maybe under the right conditions could support life. So this begs the question about how unique or commonplace the Earth is in our galaxy. While there's so much we don't know about exoplanets, while we are pretty far off from discovering alien life of any sort, we can measure the masses and radii of these planets and say something about their composition. And if those compositions mirror their host star, like they do for the planets in our solar system. Now, there are a very large number of parameters that determine if a planet is habitable. There's a lot that goes into that, let alone inhabited by aliens. But the one that we hear about most commonly is temperature. A planet has to be just the right distance from its host star in order to have liquid water and therefore life. But in order to have liquid water or life, a planet also has to have an atmosphere. And an atmosphere is mostly formed and maintained through actually being outgassed from the interior of the planet itself, which means you need some type of interior atmosphere exchange. And on the Earth, we have this through plate tectonics. And if you manage to form a planet that has an atmosphere and plate tectonics, it's also going to need something to protect that atmosphere from being eroded by its host star's radiation. And so it needs a strong magnetic field. On the Earth, ours is a dynamically generated magnetic field from the core of the planet itself. So the composition and internal structure of a planet is what enables all of these conditions that are essential for life to form and evolve. And this is what distinguishes planets like the Earth from planets like Mars. Mars most likely had liquid water in the distant past, and it even potentially could have developed life forms as well. However, its core was too small to maintain a magnetic field, and as a consequence, its atmosphere was eroded by stellar radiation, and it becomes the uninhabitable planet that we see today. Meanwhile, the Earth has a nice cozy atmosphere that's protected by a strong, dynamically generated magnetic field, and we safely have a habitable planet. So we have many things to thank for our ability to have such a wonderful planet, and the internal composition of the Earth is actually one of the most fundamental. An alien astronomer that was observing our solar system would be able to determine that the Earth is habitable and that Mars is not for several different reasons. One, if they had a really, really amazing spectrograph, they might be able to see that the Earth's atmosphere shows signs of life, while Mars not only doesn't show signs of life, it doesn't have an atmosphere in the first place. However, they could also maybe deduce this by measuring the density of each planet and the size of the iron core, and concluding that Mars likely wouldn't be able to support a magnetic field, so let's not bother look for life there. And while we can't quite achieve atmospheric spectroscopy for the atmospheres of rocky planets yet, with our current technology, we absolutely can measure their density and particularly measure the masses and radii of these planets. So for most exoplanets, we actually can't see them at all. And absolutely everything we know about them, their mass, their size, their temperature, is determined from how they affect their host star. So to measure the mass of a planet, we use a technique called radial velocities. So planets have mass, and as they orbit their host star, they exert a gravitational pull on the host star, and it causes that star to wobble around the very center of the system. And you can imagine if you were an observer looking at this edge on, the star would appear to move towards and away from you as the planet orbits around it. And we're able to observe that through the Doppler shift in that star's spectral lines. So the bigger the planet and the closer that it orbits to its host star, the bigger this wobble and shift that we're able to see. Typically to measure this, we use large ground-based spectrographs. The two I'm most familiar with are Gemini North and the Keck telescopes on Mauna Kea. Oh, yeah.
I was going to ask, what do you do if there's more than one exoplanet?
Oh, so most systems are multi-planet systems, and basically you'll see the kind of a combination of all of the planets wobbles on the host star. So you'll see one, if there's like a giant planet that orbits outer, you'll have one big sine wave, and then if there's a smaller planet more inwards, on top of that, you'll see a small variation within that. Yeah, it can get kind of complicated. And in order to measure density, you need mass and the size of the planet. So we measure the radius by watching it transit in front of its host star, and we measure the dip in brightness that we see. The larger the planet, the more of the star's light will be blocked as it passes in front, and the bigger the transit depth. We typically observe this using space-based telescopes, such as our dearly departed Kepler, may she rest in peace, and the Transiting Exoplanet Survey Satellite. So with these mass and radius measurements, we can now estimate the composition of a rocky exoplanet. So here is a planet with a similar composition to the Earth of roughly 30% iron and 70% rock. And so any planet with that composition would fall along this line at a given mass and radius. This is the projected curve for a planet that has no iron core, just silicate rock, the least dense rocky planet you could imagine having. And planets sitting above this line would likely have a thick gaseous envelope, a thick atmosphere, more similar to Neptune or Uranus than the Earth. And on the other extreme, the most dense rocky planet you could possibly have is one composed entirely of iron. And if you see a point that would fall below this curve on this graph, it would likely have to be more dense than iron. Now, is it possible? And have I read certain kind of more sci-fi articles suggesting that these could be made of ultra-dense uranium? Sure. Or it could be a bad measurement, and it's likely made of something normal, like iron. So this shaded region represents the expected diversity. Oh, it doesn't show up well. Okay, imagine that region is pink. And that would be the expected range of diversity of compositions you'd expect for rocky planets. And here, are the exoplanets that we have measured to date. And we can see that planets not only span this full range, but some do appear to be less dense than rock and likely host gaseous envelopes, while others appear to be either 100% iron or slightly more dense. So my first question when looking at this spread is whether or not this diversity is real and rocky planets are truly this diverse, or if we simply have inaccurate mass and radius measurements for one reason or another. So to test this, I targeted a sample of planets that span this entire range from really low density to really high density in order to measure more precise mass and radius measurements. So this is work I conducted in grad school at the University of Hawaii. And not only does Hawaii have the coolest hikes and beaches and shevais and poge, etc., but it also has some of the world's best telescopes on Mauna Kea. And so I was lucky enough to be able to use both Gemini North and Keck to collect around 300 radial velocity measurements for 7 different planet hosting stars over my 4 years. And while I indeed did get to go to Mauna Kea observatories with my classmates, I did the vast majority of my observing from my laptop in my bedroom. And so that means that I spent roughly 300 hours controlling the world's largest optical telescope from my bedroom in my pajamas all night. And my observing portal tells me that I collected around 8 trillion photons in this time. And let's see what 8 trillion photons can tell us about the universe. So these were the masses and radii of the planets before our study. We see, one that appears to be really low density. Oh, you can't see my mouse. Okay, the red one appears to be really low density, and these two on the end appear to be really high density of 100% iron, often called supermercuries. And I'll spare you the gory details of measuring these masses and radii, and here are the results. And I'll flip back and forth for just a moment and let you come to your own conclusions about this data. But my conclusion about this is that every single planet moved closer to this Earth-like composition line than it was at before. And in particular, those 2 really high-density supermercuries moved far more close to the Earth-like composition line. This suggests that planets are perhaps not as diverse as we once thought, and that these planets with really high or low densities aren't real, and they were the result of inaccurate mass and radius measurements. I know this may not seem like much, and it's kind of the result you'd expect, but it was actually pretty controversial. And so while observers had been declaring these detections of these extremely iron-rich supermercuries, and a lot of popular science sites love to run with articles about these worlds, planet formation theorists were really struggling to explain how they could even exist in the first place. And most people who run simulations where you smack planetesimals together and try to form planets and explain the diversity that we see, they couldn't form planets bigger than the Earth that were the same density, the same iron composition as Mercury. And in fact, most people agree now that you can only form very small planets, like Mercury, that are enriched in 70% iron or more. And so I demonstrated that most of these claimed supermercuries are not that iron rich, and in fact have Earth-like compositions. And it's not just me. Several of my colleagues have also discovered very similar things, sometimes for the same planets, sometimes for different ones. And the progress of our field has shown that indeed most planets seem to be Earth-like. And so if most planets seem to be Earth-like in composition, how does this relate to their host stars? Carl still wants to know. And so in order to compare planet and host star compositions, we need to look at the spectra of the host star. Oh, the graphics are not rendering well. I'm sorry. So we take a spectrum of the host star, we look at the absorption lines of different elements in its atmosphere, and from that we can get an abundance ratio for iron and then rock building abundances such as magnesium. We'll use magnesium as the tracer here, but you could also do this with silicon. You then turn that abundance ratio into a mass ratio of iron to magnesium and say, okay, what is the ratio of the masses of these 2 elements present in the stellar atmosphere? And then you can kind of build a planet assuming that same ratio. So you can take the amount of iron and then the amount of mass that would be present in rock if it had that amount of magnesium in it, and say, okay, this planet would be composed of 70% rock, 30% iron. Those are just the Earth's numbers that I could come up with off the top of my head. And then we can compare them to the masses and radii of the planets. So we can directly have a measured comparison between star and planet compositions. On the x-axis here, we have the stellar composition. So this is the iron fraction, iron mass fraction that you see from the spectroscopy of the stellar atmosphere. And on the y-axis, you have the iron mass fraction is predicted from the mass and radius of the planets. And here are the solar system planets on this chart. So we have Venus and the Earth in the middle, and Mercury way up top, much more iron rich, and Mars slightly below, slightly depleted in iron. And this dotted line is the one-to-one line. So this is where you'd expect every planet to fall if it inherits the exact same composition as its host star. And so as you can see, Earth and Venus have pretty much the exact same composition as the sun. Mars is slightly iron depleted relative to the sun, and Mercury is greatly iron enhanced. So when I plot exoplanets on here, if it's above this line, you know that it is more iron rich than predicted by its host star. And if it's below this dotted line, it is iron poor relative to its host star. And this is what we see for the population of rocky exoplanets. These colorful points are the ones that I just barely updated their masses and radii for. And it's really hard to see much from this cluster of points with large error bars. But 75% of these points have the same composition as their host star to within 1 standard deviation uncertainties. And that means that 75% of these points have their error bars overlap with this dotted line, this one-to-one region to within 1 error bar. And this is similar to the ratio that we observe in our own solar system. 75% of the terrestrial planets mostly agree with the composition of the sun, and 25% don't. And speaking of Mercury, we don't see, again, many planets up here as dense as Mercury. This orange guy, you can't see my cursor, the orange guy, Kepler 100, is a little iron rich, but it has huge uncertainties. We have no idea if that guy is, nearly 100% iron or 20. So speaking of these large error bars and small sample of planets, the obvious next step is to fit a line naturally. And when we perform linear regression to this, we see that the best fit line in purple is very similar to this one-to-one dotted line, especially within the shaded uncertainty region. And so, yeah, it's a small sample, and these are big error bars. Exoplanets is a very new field, and we're trying to investigate these fundamental relationships and draw these pretty profound conclusions with a sample of about 20 planets that have 30% uncertainties at best. So as we discover more planets and measure better masses and radii, this relationship is bound to improve. However, despite all of this uncertainty, it seems that out of all of the bizarre and interesting possibilities for rocky exoplanets to be in our galaxy, for the most part, they're Earth-like, and that they have Earth-like iron to silicate mantle ratios. And not only this, it appears that the majority seem to have the same ratio of elements as their host star, as one would expect if they're born from the same primordial soup. And in some ways, this is a rather mundane result, right? This is what one would naively expect to find when we're looking outward to the cosmos from our own solar system. I've occasionally felt disappointed that I did not discover something more interesting and exotic and unexpected throughout my career. But on the other hand, most planets having Earth-like compositions means that there's a higher potential for these planets to be Earth-like in other ways, such as they could have plate tectonics, they could have magnetic fields given a sufficient enough core size, and it makes it more likely that these planets could have favorable conditions for habitability. And while it could make habitability more likely, an Earth-like composition certainly does not guarantee that a planet will be habitable. Let's revisit again what alien astronomers would see when observing the solar system. Except this time, let's give her a large ground-based spectrograph and a really cool space-based telescope to measure its masses, precise masses and radii of the solar system objects. And of course, let's give her some pajamas because that's how all good observing is done. And she would very likely measure identical masses and radii for the Earth and Venus when looking at the solar system. And she would most likely determine that these are twin planets. She would also likely determine that both of them are in the Goldilocks habitable zone around the sun, and think that both of these planets are likely to host life and that they could be habitable. However, all of us in this room know that Venus is an extremely toxic planet filled with sulfuric acid and snows metal and has crushing atmospheric pressure that will even destroy all of the probes that we send there, let alone life forms. So while having an Earth-like composition can make it more likely that a planet will be habitable, it certainly does not guarantee that the outcome will be a habitable planet, let alone an inhabited one. So while we've discovered thousands of Earth-sized rocky planets across our galaxy, we still only know of one that is truly habitable. And I would be remiss to end a talk about the uniqueness of the Earth in the year of our Lord 2026 without revisiting another classic Sagan quote and showing the image of the Earth as taken from the Voyager spacecraft as it was leaving the solar system. Look again at that dot. That's here, that's home, that's us. Everyone on it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was has lived out their lives on this dot. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all the presidents and fascist regimes so that in glory and triumph, they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by inhabitants of one corner of this pixel on the scarcely indistinguishable inhabitants of some other corner. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. Like it or not, for the moment, the Earth is where we make our stand. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish this pale blue dot, the only home we've ever known. Thank you, and I'll take questions.
Okay, so thank you for the speakers. So now we will move into like the panel discussion stuff.
Okay. And I can leave
oh no, just leave it.
Okay.
Spoilers.
Okay. Never mind. I wasn't sure it was.
You guys can just stay here.
Okay.
Oh yeah, maybe you should turn that up.
Yes,
Yeah,
I will.
it's gonna be
Yeah. Some weird stuff.
Yeah.
Hold on, let me
I'm over here.
it kind of had to talk like weird. Is that good? Yeah. Okay. All right. Yeah, it's not gonna be too loud, but okay. So now it's discussion time. So feel free to just raise your hand, and then the speaker can just like pick who wants to. Okay, well, I'm sorry.
Yes, a lot of planets in so-called habitable zones, the stars emit dwarf, therefore they have too much radiation to actually habitable. So the term habitable zone is somewhat misleading.
Very true. And in fact, none of those 200 habitable planets, all of them are around red dwarfs. There are none around sun-like stars because our instruments aren't sensitive enough to detect them yet. And so actually none of the planets that I look at are even remotely close to being habitable. They all are really close to their host star. They're really hot, over 1,000 Kelvin, 2,000 Kelvin. And what I'm projecting from this is simply the trend that if we find that most planets that are close to the sun have the same, are all Earth-like, if everything seems to have an Earth-like composition, it's not a crazy assumption that then if we find one in the habitable zone, it will have it like that. So it's overall trends. It's not specific ones yet.
Can I add to those?
Oh, yeah.
So another like follow-up question for you actually on that. I remember hearing like hopes that maybe life could survive in an ocean in a habitable world around a red dwarf, because as you mentioned, the problem is X-rays. Like there's too many X-rays in the habitable zone. But if you're like a couple meters inside water, you could be fine. So do we have examples of planets that for which the density would be actually comparable to an ocean planet in the habitable zone?
So answer is yes and no. The answer is yes, because there are planets that could have a water-rich rocky composition in the habitable zone, but no, because we can't determine that. Once you start adding in all those components, it's really hard to determine what the planet's actually made of and like how much give and take there is between core and mantle and ocean and then atmosphere, because it could just have a thick atmosphere and then who knows.
Nice. So there could be ocean
could
worlds. We don't know yet.
Thank you for your presentations of you both. This is for Casey. Every now and then in the mainstream media, I would read that, yeah, they discovered a meteorite from Mars. How do they know that this first thing is a meteorite and not just a simple rock? And secondly, how do they know it is from Mars?
Little outside my wheelhouse, but it's a great question. I think largely from the composition, it'll have a slightly different, it won't be the same composition as the rocks that we have on Earth's crust, and it will be similar to what we know Mars is made of from the probes and the landers and everything that we've sent there. It would have the chemical signature of being from Mars.
Yes, it's so for Casey. We compared the densities of these exoplanets compared to the planets in our solar system, but honestly, they're just like this general trend of the moons in the solar system are less dense. How would you compare them to the moons? That's a general question, actually.
Yeah, it's a great question. So the moons are generally less dense than the planets, and that's also probably because especially our moon was formed through a giant impact. And so these two planetesimals had the same composition. The core material, the iron, was more left in the Earth. And the moon, as a result, has almost no iron core. It's like 10% of its mass is iron core. We do see a lot of planets that appear to have either no core, very little core, but again, you get into the uncertain territory. It could have a normal size core and a thick atmosphere, and it would have the same density. You get these trade-offs between low density and high density components. And once you get 3 or 4 different types of components in there, you can't separate the two out anymore. So could be, but we don't know for sure. There's 3 people. Let's start here.
How do you actually measure core?
So it's from the combination of the density of the planet, the mass and the radius, and also a model. So basically I run a computer model that builds a core and a mantle for a planet. And the reason you can't just use the density is because as the planets get bigger, the materials get more and more compressed. And so a planet that's twice the size of the Earth would be much, much more dense, even if it has the same composition of 30% iron, 70% rock. So you have to solve what's called equations of state for the different materials and the different temperatures and pressures, and that's how you know.
These are measured from the wobble of the star, right?
Yes.
Yeah, both of you have talked about the composition of your
planets or exoplanets, and it's always iron, silicon, and magnesium, right? Is that because we expect that because this is what we're familiar with here? Or is that just, oh, that's what we're finding?
I mean, so yes, we have to make a few assumptions that the minerals in the planet and the ratio of those, you know, most of the Earth is made of MgSiO2 or MgSiO3, and you have to make an assumption that the exoplanets are similar to the Earth in that way. So many assumptions goes into it. They might be bad assumptions. We don't really know yet. And so I would say a lot of the assumptions that I make are based on it being similar to the rocky planets in our solar system. And then you get to have the fun, weird compositions.
Oh yeah, because that's the follow-up is that in my case, they are gas giants. So the compositions are really not the same as these rocky planets. In our case, we have like methane, water, carbon monoxide, carbon dioxide, we have ammonia, we have all kinds of weird gases, and sometimes even like precipitation in the form of water or iron clouds, iron for you, but we have all kinds of weird elements, and there was one example that was really cool. So we found this brown dwarf that was called the accident because it was found by accident during Backyard Worlds. Someone was investigating an infrared image for something completely different, and they saw a brown dwarf moving super fast, so fast that no one had detected it, even in the Backyard Worlds project. And this was one of the users of Backyard Worlds, so he was kind of used to seeing brown dwarfs in these images. So he was like, what is that in the corner of the image? So we actually studied it in details, and we were like, oh, this is a very, very weird one. The color is very weird. This is why we had missed it. And we observed it with the telescope. And in this case, like I reduced the spectrum, which means like we got the data from the telescope and you have to like do all kinds of operations to really get the spectrum. And when I saw it, I've seen thousands and thousands of brown dwarf spectra. When I saw this, I was like, is this a brown dwarf? I was like, and we jokingly called it the alien megabase. And then we had phases where we wondered, is this actually a white dwarf or a kind of weird star? But no, it's a brown dwarf, and it's the oldest brown dwarf we've ever found. And its composition is so completely depleted that there's no clouds whatsoever in this object. And it's the only case where we were ever able to detect a very weird molecule called silane in its atmosphere. So this is one example where we had a spectral signature, like these line shapes in the spectrum, and we didn't know what it was. And we talked to chemists, we dug in databases of actual gas compositions and what are their spectral signatures. And we ended up like getting James Webb Time on it to get a really, really precise measurement. And it's really like out of question that it's anything else than silane. It matches really perfectly the absorption from silane and nothing else. And it was actually a big question why we couldn't see silane in Jupiter for a while in the solar system. And people had theorized that it's probably because the silicon gets captured in clouds deep in the atmosphere. So there's no more silicon left to form this molecule called silane in the high atmosphere. And that was kind of the working hypothesis. But now we had this example where there's no clouds and there's silane all of a sudden. So it kind of really gave credence to this idea that this is why we don't see silane in Jupiter. So just to demonstrate that sometimes we don't even know what we're looking for, and we have just spectral lines, and we have to do a mystery hunt to figure out what the element we are looking at, what's the molecule or the element.
So, Casey, you said that you use, well, it's for both of you actually, yeah, it's a follow-up of one thing that you said. So you base yourself upon the composition of the own solar system, the planets and all. But how do these compositions of the planets compare to perhaps of the nucleosynthesis, so photosynthesis? like I understand that there are a lot of molecules that aren't formed in the stars, but for example, in terms of the amount of silicon that is created by the stars versus the amount of iron, how close is to what we have inside of it?
So I think to answer that, there's kind of two schools of thought when it comes to modeling these Earth-like planets. And people tend to, you just have to, they're both bad, you have to pick a poison. So you can either assume that the mineral composition of the actual rock itself, the MgSiO2 or 3, your Bridgmanites and your, all that, the minerals in the Earth are in your exoplanets are Earth-like, or you have to assume that they match the ratios in the host star. And that often requires them to have a mineral structure that's not one that we observed yet on Earth and don't fully understand its properties, excuse me, and its compression and etc. I tend to pick that we assume it's like Earth. A lot of people pick the other. The result, it doesn't really matter because the error bars on these points are so large that no matter what you do, it's kind of within the uncertainties of the massive radius of these planets anyway. Pick your poison. It's okay.
It will be a problem someday.
I know, well, I think that many of these platinums are observed in binary pairs. I don't know if that's true, but yeah, and if so, like, how do those binaries get formed? And then also, do you guys look at these as possible harbors of a technological civilization? Like, considering that they'll stay warm for 10 trillion years?
Well, if you tell Avi Loeb about planets, he will probably find a way to suggest that. But I mean, it could be somewhere where there's life or any type of life if you have a suitable moon around them. Probably not in their atmospheres because there are cases atmospheres like Jupiter. Except if you go to the extreme cases like the gravitational lensing discovery I talked about, like if you go even smaller, you could have rocky planets. We just are not able to detect them. And I would not be surprised if there are many rocky planets floating out there. They're just super, super hard to see. We don't have the technology to see them. So on rocky planets, then yeah, maybe you could have something subsisting from the residual heat of the planet. It wouldn't be as hospitable as Earth, obviously. But yeah, you could imagine all kinds of scenarios where you have like technological like civilizations there, but we just don't have any means to measure that yet. In the far future, maybe, but we're basically blind to that stuff right now. And as to your other question about binaries, they're mostly not found as binaries, although we do have one example, which we think is a planemo. It's a binary, and each component has about 6 times the mass of Jupiter. And this is a very good question. How do you form this? And it would be very hard to form a massive gas giant planet around a star in a binary planet-planet configuration, and then eject it and then keep the binary configuration. That would be super hard and weird. Although you could form this very easily like a star, because we know stars form like binaries. So these binary planemos are strong indication that they might have formed as like stars. There was also this recent paper claiming a lot of binary planemos called jumbos. They gave them this name in, I think it was in Orion. It's a very, very young star forming region. It's a bit of a controversial result, and myself, I'm very skeptical of it for one big reason. In these regions of young star form, like where you have a lot of star formation, and when they are this young, you also have a ton of dust and a ton of gas, and you can easily catch a binary star that's behind some dust, and the color of the star will appear extremely red when it passes through the dust, and it can even appear infrared because of the extinction of the dust. So if you just see the light at one wavelength, it looks like a planemo. But then you need to do the detailed study, get a spectrum to see the the detailed atmospheric composition, which has not been done yet with any jumbo object. So you have two possibilities, and one is very mundane. You have just binary stars that are behind an extinction cloud. And I think one big problem that we see in these recent discoveries is that we have this new amazing tool, James Webb, which allows us to peek through ever denser clouds and see ever more reddened stars in the background. So we can easily get excited and be like, oh, we found a ton of planetmos all at once, and we're just getting better at seeing through these clouds. So we gotta be very careful in interpreting that. But I'm expecting we will get spectra for these objects quite soon, so we will know.
I have a few questions, but I'll get my first. I know that the Nancy Grace Roman Space Telescope is going to get launched pretty soon, and that one is specifically for exoplanet discovery. And you also said that the rocky planets that we have so far discovered are around red dwarfs. I was wondering if with the launch of the Space Telescope, we'll be able to discover more around sun-like stars. Would that be possible?
The answer is absolutely, and Roman is going to do so many amazing things. Gravitational lensing is, so it uses the technique that you briefly mentioned called gravitational lensing, which is a little bit outside of my wheelhouse as to what I normally know how to do, but it's going to have the power to discover really small planets that orbit much further from their host stars that you'd normally be able to measure with radial velocities and transits, etc. The downside of it is that it's going to be really hard to do follow-up characterization of these planets because, like he said, they kind of pass through and we get that brief moment and we measure them, and that's all we're ever going to be able to get for those planets mostly. So it's really going to depend, but it's going to discover a lot that could be in the habitable zone.
Sorry, that's a question for Jonathan. I was wondering if it's possible that there are exoplanets orbiting around the brown dwarfs. Is that it must be pretty hard to observe those because they don't give off light.
Yeah, so that's the main problem. So yes, there could be, or moons. So that's yet another thing I'm excited about. When we start finding these, we're gonna have even less names for them because they're gonna be even weirder and have less definitions. We actually do have one example where the host is a brown dwarf. It's about 80 times, 70 or 80 times the mass of Jupiter, and the companion is like 10 or 12 times the mass of Jupiter. So it's a brown dwarf and a whatever planet, not planet, because it's a brown dwarf host. So we are starting to see hints of that, but as we are able to detect smaller and smaller companions, I think we might find some. We did find some brown dwarfs which have disks, so the very young ones, and this is a sign that you can form something with these disks potentially. But we don't yet have the precision with our instruments to actually find companions. This is going to be extremely hard, but some people have started trying. So applying the method of, for example, radial velocity, which Casey explained, to brown dwarfs is so hard because they're very faint and you need super precise infrared instruments, which is like another layer of difficulty. You could get more lucky with transits and just staring at many brown dwarfs and see dips in them. The problem we have is that we have about 3,000 brown dwarfs and they are located in random directions on the sky. So we can't do the strategy like Kepler of staring at like millions of them at once and just waiting for one transit, waiting to be lucky. We just have 3,000 and we would need to observe in 3,000 directions at all times. So if we would like put all the telescope time on Earth dedicated to just doing that, we might find one, but I'm not sure that everyone would agree to do that.
Is there a method to find exoplanets by looking at the stars head on? Like the planets run around the stars in a plane, right? Usually the transit method or the radial velocity method is you look sideways. Is there any method to find exoplanet?
So that method is called astrometry, and you basically be looking to visually see the star move in the plane of the sky. It's so hard to see. It's not a very productive method, but it's really hard to see.
Yeah.
Yeah.
So with the final data release of Gaia, we might get a lot of these exoplanets actually, because Gaia has an incredible angular precision for the measurement of positions of stars. And we don't yet have all the individual data points from Gaia for each star, giving us the exact location of the star at every epoch. They just measured some things that they gave us, but they haven't yet calibrated the full data set for us to play with. And when they release it in, it's going to be the 4th data release, the next upcoming one, which is in about a year. I expect that we might find a lot of exoplanets by astrometry. I don't think there is even one discovery right now that's been made from astrometry.
I can't think of one.
Yeah.
I didn't want to claim that, but
I know some have been detected, but they were known from different methods before. So there's only a few that were actually that some people pulled this off, like knowing that they picked their planet that would work best with this. But with Gaia, we will have the necessary data to look for that for more than 1 billion stars. So we will probably find some, the easiest cases.
Why did you say we need plate tectonics to have an atmosphere?
we don't need plate tectonics, but for most planets like the Earth, our atmosphere is what we call secondary. It's not primary or primordial. So basically, if a planets are formed in this big cloud of gas and dust, and planetesimals smash together and they get a bunch of gas, and whatever gas is around that planet initially is called a primordial atmosphere. Ours was almost certainly wiped out from stellar radiation. And we actually think this is the case with a lot of exoplanets. The atmosphere that we have was from volatiles that are trapped within the rock of the Earth itself. And you don't need something like plate tectonics to outgas an atmosphere. You know, if the surface of the planet is magma and it's liquid magma, you can have this as well. But there needs to be some type of exchange between the interior of the planet and the exterior of the planet in order to form that. And so plate tectonics is one method of doing this.
So I had a question for you, Jonathan. Is there a limit to the age of the planimals you're able to detect? Is there essentially, are our senses like sensitive enough that irrespective of the age, the radiation law gets so slow beyond a certain point that we'll always be able to detect, or we have essentially a threshold over which you say, yeah, the planet was going to be so cold, there's no chance for us?
There's not really a threshold. We have this example called WISE 0855 that is actually the fourth closest whatever to the sun, the closest not star, but so you have Proxima, which is the nearest star. You have Barnard, which is the second nearest star. Then you have Luhmann, which is a Luhmann 16, sorry, which is a binary brown dwarf. And the fourth one is WISE 0855, which is probably around the mass of Jupiter. And we don't know its age, but it looks kind of old. And it's incredibly faint and cold. It's at almost room temperature. It's close to 0 degrees Celsius, actually, in its upper atmosphere. And it's likely that there's ice crystals if you go deep enough in the atmosphere, or snow, but it's like a gas planet. It's it's a very weird object, and it's one of our closest neighbors. Discovered in 2015, if I'm not mistaken. So very recently. And some of my collaborators spent 4 entire nights with a 6.5 meters telescope on Earth with an infrared detector to try and detect it, just the dot. And they were barely able to. You basically have to be in space with an infrared detector to see it. And this is the fourth closest system to us. So this is mind-blowing to me that this is so close to us, and it suggests there might be a lot of them. The problem we get at these old ages is that we cannot trace back their siblings. It's too old for the group to be still moving in the same direction. As they go around the Milky Way, every orbit takes about 250 million years. And just after a few orbits, they get spread out completely. So WISO 855, we have no idea what its age is, but we suspect it's in the range of 1 to like 12 billion years, just based on the fact it's in our galaxy. But then the mass range that we get from that is anywhere between 1 and 15 times the mass of Jupiter. So it's most likely a planemo, but we're not sure. And this is the classical problem we hit for the older objects. They are first very hard to detect, but second, the age that we have for them is very imprecise. So the objects for which we have very precise ages, the best scenario in terms of the oldest ones would be in open clusters, because these remain together for a longer time. But most old open clusters tend to be very far from us, so they're not good targets yet. So the oldest ones we have are probably 500, 600 million years, which is not very old. So they're still relatively warm, the planemos we find in them. But yeah, we have also this problem of faintness. It's very, very hard to detect them.
Planemos form rings, and if so, how common are they?
How come what? Sorry? Oh, how common are they? Sorry, okay. So planemos can probably form rings, but we don't have any means to detect these. So it's a bit related to the question of do they have moons, because moons can, the fragments that either you can have moons colliding, creating these rings, or they can be left over from the disk, but we just don't have any way of measuring that. It's beyond our technology.
Question.
So do you mean like practical applications in everyday life, or? Right, this tends to happen so randomly, like with discussing random ideas with people. You find like an example. Does he have like one?
No.
I like that.
I would tell you something fun,
Doesn't
but
happen.
no.
But I'm sure some of these things must have happened, like if we really dig in our head. But yeah, this typically happens when you get like big conferences, lots of people talking about their topics, and then new ideas emerge and new topics of research emerge. But it's rarely like one single person that's like, aha, I'm gonna do this. And for example, with the radial velocity, the transit, the astrometric way of detecting planets, these have been like theorized a long time ago. So there's been so much work done in like imagining ways to do this. So as we like do our studies in physics and astronomy, we learn about all these things, and we even know ways to look for moons that are not really applicable yet because of the current technology. So it's we're kind of swimming in ideas all the time. So it's very rare that we just come up with a new detection method out of the hat or something. It's very rare.
Okay, we'll take one more to just kind of.
In your study using the cat observatory, there's actually two.
Yes.
Do you either or? Do they offer a unique view into space because there are two of them?
So it's funny, both of my preferred favorite telescopes, Gemini and Keck, both have two. Keck has Keck 1 and 2 on Mauna Kea, and Gemini has Gemini North and Gemini South. It's the twins. But none of these telescopes operate in conjunction with each other in the slightest. It's not like you can use them as like an interferometer or anything cool like that. I always use KEP1 because KEP1 has both the high-res spectrograph and it also has the Keck Planet Finder, a brand new spectrograph. They just have the instruments that I like. Keck2 has instruments that are, there's some ones that are better for galaxy detection, all sorts of stellar astronomy. And I use Gemini North because I'm in the northern hemisphere.
I use both north and south to see both hemispheres because ground doors and planets can be anywhere in the sky. So I like having access to both.
Okay, well, let's think. And for the next public talk, it's going to be on February 19th. So it's going to be 7 p.m. in Trottier building. So it's the one past Rutherford. So it's not going to be this room. And we'll have a talk from a professor from France about how nuclear physics advanced modern medicine. So thank you, everyone.
Like,